So at the heart of modern physics, you've got these two giants. On one hand, there's general relativity. It's our beautiful description of the large-scale universe, planets, stars, galaxies, all moving to the rhythm of gravity. And on the other hand, you have quantum mechanics, the rulebook for the tiny, strange world of atoms and particles. For almost a century now, the fundamental conflict between these two ideas has been one of the biggest unsolved puzzles in all of science.
Now, we have a pretty good quantum description for gravity when it's weak, like the pull you feel from the Earth. But that picture gets really blurry when we look at the most extreme places in the universe. What's going on in the intense gravitational field of a black hole? Does gravity still play by quantum rules there, or does something entirely different happen? This is the gap in our knowledge we're going to be exploring today.
Okay, so let's be really clear about where things stood before this paper. Physicists were already confident that weak gravity could be described with quantum mechanics. The big missing piece was whether this quantum nature is universal. In other words, does gravity have to be quantum everywhere for it to be quantum anywhere? Now, this paper doesn't claim to have the final theory of everything, but it does offer a powerful argument, and it's all built on one simple demand, that our laws of physics have to be logically consistent with themselves.
So let's dig into the logic here. And as we go, this is the question you should keep in the back of your mind. We're not looking for a flashy headline. We're trying to understand exactly what new piece of the puzzle has been put on the table, and just as importantly, what hasn't.
You know, when you're trying to probe a question this fundamental, you can't just go and build an experiment in a lab. So instead, physicists turn to one of their most powerful tools, the Gedanken experiment. It's just a fancy German word for a thought experiment. It's a way to push our current theories to their absolute logical extremes, just to see if they break.
This particular thought experiment involves two observers, who we'll just call Alice and Bob. Now, the most important rule of the game is that they are space-like separated. This is a very specific term from relativity, and it basically means they are so far apart that no signal, not even light, has enough time to get from one to the other during the experiment. Whatever Alice does, Bob can't possibly know about it.
Okay, so here's the basic setup. Alice takes a system of masses, you can picture a tiny dumbbell, and puts it into a quantum superposition. That means it exists in two different orientations at the exact same time, a classic bit of quantum weirdness. Now, each of those orientations creates a slightly different gravitational tidal field. And far, far away, Bob's job is to try and figure out which state Alice's system is in without any direct communication.
And this is where the paper's big new idea comes in. In older versions of this experiment, Bob's detector was just some simple particle. But here, the researchers used something way more exotic, a rotating black hole. The idea is that this black hole will wobble, or precess, a little bit differently depending on which of Alice's two gravitational fields it feels. And Bob's job is to measure the gravitational waves, the ripples in spacetime, that come off of that wobbling black hole.
So this whole setup, it's incredibly clever. And it's designed to do one thing: lead us straight into a paradox if we make one simple assumption. And that assumption is that the gravitational waves Bob measures are classical. You know, like simple ripples on a pond, instead of being quantum. If that were true, the universe would literally contradict itself.
Right. Let's trace the steps here. If those gravitational waves were classical, then Bob could, in theory, measure them with perfect accuracy. By analyzing those waves, he could instantly figure out how his black hole was wobbling, which would immediately tell him which state Alice's system was in. But hang on, remember, they're space-like separated. This would mean information traveled from Alice to Bob faster than the speed of light, and that, well, that breaks causality, one of the most basic rules of the universe.
So, okay, we've hit an impossible result, but this isn't a sign that physics is broken. The solution to this paradox shows that relativity and quantum mechanics are working together in a really deep, subtle way. It turns out, the universe has its own kind of fail-safe built right in. And here's the escape hatch. That paradox, it only happens if we assume the waves are classical. The moment we accept that they have to be quantum, the whole problem just dissolves. The need for everything to be logically consistent basically forces us to conclude that gravitational waves must have quantum properties.
So what does it even mean for these waves to be quantum? Well, it means they're subject to quantum fluctuations. You can think of it as a fundamental, unavoidable jitter or noise that's woven into the very fabric of spacetime. It's not a mistake in our equipment, it's a real, basic feature of reality.
And here's the truly brilliant part, the core insight of this paper. This quantum noise isn't just random in its effect, it's perfect. It's exactly the right amount of fuzzy. It blurs the gravitational wave signal just enough to stop Bob from telling the two possibilities apart in the short amount of time he has. It's nature's way of enforcing the cosmic speed limit.
So the researchers put this into formal terms with two competing conditions. For the paradox to happen, two things have to be true at the same time. 1. Bob needs to get a clear enough signal to tell the difference. And 2. Alice's quantum system has to stay perfectly isolated from the outside world. And what the math shows, the core result of the paper, is that you simply can't have both, not as long as they're space-like separated. The universe literally makes it impossible.
So you see, this thought experiment is way more than just a neat little academic puzzle. By demanding that our theories don't produce absurd results like faster-than-light communication, it serves as a powerful check on our understanding, forcing us to refine how we think gravity has to work.
And that actually has huge implications for anyone trying to build a new theory of physics. It strongly argues against any kind of hybrid model, theories that suggest maybe gravity is classical near a black hole, but quantum somewhere else. For the universe to make sense, this result suggests that if gravity is quantum anywhere, it has to be quantum everywhere.
The authors themselves state their conclusion very precisely. They say that to keep relativity and quantum mechanics consistent with each other, you have to accept that gravitational waves are quantized. And most importantly, this has to be true even for waves that come from situations where gravity is incredibly strong, like the black hole in their experiment.
Okay, so let's come full circle, back to that guiding question we started with. What does this study actually demonstrate? And where do its conclusions stop? It's really important to be precise about the takeaway here.
Well, based strictly on this paper, we can say that the need for logical consistency is an incredibly powerful tool. It forces the conclusion that gravitational waves must be quantum, and that this has to be true even for waves born in the intense gravity near a black hole. Now, does this give us the final theory of quantum gravity? No, absolutely not. That search is still very much on. But what it does do is eliminate some possibilities and put that whole search on much, much firmer logical ground.
So while this helps lock in one piece of the puzzle, it kind of deepens the mystery in other ways, right? It forces us to accept the quantum nature of the most extreme objects we know of. And it leaves us with this final, tantalizing thought. If the universe works this hard to protect its own logical rules, down to the quantum jitter of spacetime itself, what other profound secrets are just waiting there for us to find?